Section 2 in Chapter 4 is called Patterns and Linear Functions. So what we're doing in this one is we're going to review a little bit about the coordinate plane. That's what you see right here. And then after that, we're going to get some vocab going and get into graphing a little bit from some situations where we're given figures and kind of review what a function is, or maybe learn for the first time what a function is, and then kind of go from there. So we're building the foundation for graphing from equations, which is a big deal for us in Chapter 5. So this chapter kind of is a building block for us, and it's very important that we understand what's going on. So make sure you're paying attention, make sure you understand. So first of all, the review of the coordinate system. I know that we've learned this before. It's like 7th grade you started to see this full blown, and then 8th grade for sure you had all of this down. So first of all, the x-axis is the horizontal axis. Okay, so I'm actually going to be very picky about how you define this. I don't want to say like the some of the things that you guys are going to want to be tempted to say, maybe the definitions that you were given back in middle school. So, if you have something in your mind and what the definition should be, and I say something different, I want you to switch that to what I say, because it's going to be relevant for us later on. So the x-axis is the horizontal axis. Let's see if I can get my pen to draw. There we go. Okay, now the x-axis, so then is the bold horizontal axis, and there's a positive direction and a negative direction. The positive direction for us most of the time is going to be to the right. So positive x, that's a positive x axis here, and then negative x axis to the left. Just like a number line that we've been drawing all the way through like chapter 3, okay? So negative was to the left, positive was to the right. Same thing here. Okay, now the y-axis, now that we know that the x-axis is the horizontal axis, we should know that the y-axis is going to be the vertical axis. Okay, that's vertical axis. So the bold axis on this graph that I have here is our vertical axis. That's our y-axis. And just like with the horizontal axis, the x-axis, there is a positive y-axis and a negative y-axis. Okay, so the positive y-axis is up, and the negative y-axis is down. And really, the y-axis is just another number line. It's been turned, so rotated 90 degrees, just like the x-axis was. We just turned it 90 degrees counterclockwise is what we would say. And that's it, okay? And they are intersecting, and where they intersect is the origin, okay? Where they cross is the origin. So where the axes cross. So axis is one, like the x-axis, the y-axis, one axis. The two axes together is plural. AXES is plural of axis. All right, AXES. So where the two axes cross is called the origin. All right, so that means that the origin is right there. Okay, now the coordinate plane. The coordinate plane is the whole grid. So the grid, remember, does not stop where we stop the grid on our screen right here, okay? It extends forever. So when we look at the axes, we see the arrows on the ends, okay? The axes extend forever in every direction. And that means that this grid actually also extends forever in every direction. Even though we only see this little bit of it, it does not stop where it stops on this page. It goes forever in every direction. So when I say the whole grid, I don't mean just what you see, I mean everything. It extends forever. It's infinitely huge. We can't possibly draw an infinitely huge coordinate plane, so we only draw like this much, okay? And then we make a scale based on how much of the coordinate plane we need to see for the interesting stuff that we need to graph. And then we make our graph. So when I say the whole grid, it is the entire infinitely huge coordinate plane, okay? Now an ordered pair is a set of numbers, okay, that's ordered. That's why it says ordered pair. They're put in a particular order to give us a location on the coordinate plane, okay? So the ordered pair is location, a location on the coordinate plane. Okay, so if you have an ordered pair, what you're looking at is a location on the coordinate plane. And the ordered pair looks like this. It's going to have parentheses around two numbers, okay? And the two numbers, if we have an x-axis and a y-axis, are going to be the x coordinate, so the x location, followed by the y location, okay? The x coordinate then is the first number, and the y coordinate is the second number. Okay, I kind of drew my arrow through the comma, so I'm going to redraw it. X comma y with parentheses around it. You have to have the parentheses around it. That's part of the notation. So the x coordinate comes first, the y coordinate comes second. An interesting little note is the reason that we draw the ordered pair x comma y is that they are in alphabetical order. Okay, this comes up in a big way in Algebra 2. We put things in alphabetical order. So we have x comma y alphabetical order. Okay, the x coordinate comes first, the y coordinate is second. Okay, so that's the idea. That's a review. Hopefully that was all review for you of the coordinate plane and all of its parts. So moving on, there's two types of variables now. Okay, there's the independent variable and the dependent variable. The independent variable is the variable that we control. Okay, if we're doing a science experiment, then this would be like if we're controlling, if we're trying to measure the plant height based on the amount of water that we give a plant or the amount of light that we give a plant, the thing that we're controlling is the amount of water that we give it or the amount of light that we give it. Okay, that's the independent variable, the thing that we control. That's usually going to be, especially in Algebra 1, the x variable. Okay, the dependent variable is the variable that changes because of what we did to the independent variable. Okay, so let me write that down. The dependent variable is the variable that changes because of what we did or because of what happened to the independent variable. And that is usually y. Okay. Now the variables don't always have to be x and y. That's why I'm saying usually x and usually y. So the independent variable, whatever it is the one that we control. And the dependent variable, whatever it is the variable that changes because of what happened to the independent variable. Okay. So basically what happens is the independent variable here causes the dependent variable here to change. Okay? One causes the other to change. So if we look at these two examples here, it says determine the independent and the dependent variable for each relation. If you just figure out what the variables are and you ask yourself what is causing the other to change, that will tell you which one is the independent variable. Okay? So the air pressure inside a bike tire increases with the temperature. The first thing you want to do is ask yourself, what are the variables? What are the two things that are changing here? Air pressure inside the bike tire increases with the temperature. Well, the two things that are changing are the air pressure and the temperature. Okay? So now ask yourself, what is causing the other to change? It says the air pressure inside the bike tire increases with the temperature. So does the air pressure changing cause the temperature outside to change? Or does the temperature outside to changing cause the air pressure to change inside the tire? The answer is the temperature outside causes the air pressure inside the bike tire to change. Okay, so that means that the air temperature outside is the independent variable. And that makes the air pressure inside the bike tire the dependent variable. Sometimes you got to think about these things a little bit. And if you do think about it a little bit, you'll come up with the answer usually on your own pretty easily. Okay. The second one, as snow melts off the mountain, the Bighorn River rises. So what are the two variables? Snow melts is one, and river rising is the other. Okay. So now what causes the other to change? Snow melting off the mountain will cause the river to rise. Yes. So this is snow melting is the independent variable. And river rising is the dependent. There's several things that will make the river rise. And just because the river is rising does not mean that snow is melting off the mountain. Okay, the river can rise because of an ice jam. The river can rise because the dam broke down in Thermopolis. Okay, lots of reasons. It could be raining down here. Lots of reasons the river can rise. All right. But if the snow is melting off the mountain, for sure the river is going to rise. Okay, that's why it's the independent variable. Okay, so some more vocab. We have inputs and outputs. So inputs are values for the independent variable, things we put in. Okay, we put water into the pot for the plants. Okay, we put light into the room for the plants. Okay, those are inputs. So vocab definition for inputs would be values for the independent variable. Okay, so those are X values. And then outputs would be what we get. From the inputs. So we put the things in, our X values, and then we're going to get something in return. Okay, those are our outputs. So those are going to be the Y values. That's the idea. Okay, put something in, we get something back. We get something out. All right, so that's the vocab. Let's see what happens next. So now we have a function. A function happens when we put some value in and we get exactly one value out. Okay, so let me kind of explain that a little bit. So let me get this definition down here first. Put some value in, whatever it is, some value in, and get exactly one value out. Keep doing that. One value out. Okay, exactly one value out. So what I mean by that is this. Let's say I have a machine, and it's a chicken nugget machine. So if I put some chicken in, I'm going to get chicken nuggets out, right? If I put a chicken in, I get chicken nuggets out. Put some other chicken in, I get chicken nuggets out. I go with some other chicken, I'm going to get chicken nuggets out, okay? As long as I put chicken in, I get chicken nuggets out. It would be weird if I put chicken in and I got like a Hot Wheels car out, okay? It wouldn't make any sense. All of a sudden, I'm putting in the same value, but I'm getting some other value out, all right? That's what I mean by this definition. Put some value in and get exactly one value out. I'm expecting to get chicken nuggets out of my chicken nugget machine. If I get something else, something is wrong with my chicken nugget machine. Okay? That's what a function is. It has an operation to do. It gives me something in return. If it doesn't do that, something's wrong. It's not a function anymore. Okay? So that's the idea. I need to get exactly one thing in return. Okay? So for any x value, I better get exactly one thing back for my y value. If I put in some x value and I get more than one y value in return for that same x value, it's not a function. All right, that's the idea. So that's what this definition means. So for every input, there is exactly one output. Okay? For every x value, there's exactly one y value. That's what this means. Now, a linear function means that if I graph it, the word linear actually has what the graph looks like in it. It looks like a line. Okay? So a linear function has a graph that looks like a line. So that forms a line. All right? Pretty straightforward definition there. So we can represent relationships and functions with tables, words, equations, ordered pairs, and graphs. We've done most of these already, so that's good. This is kind of a review. We're just maybe sort of formalizing things right now. So in order for a relation to be a function, first of all, in order for a relation to be a function, what we need is no repeated x values. Okay? If you have no repeated x values in the stuff that you're given, then you can claim that it is a function. If you have repeated x values, then you probably don't have a function. Okay? Because if I have some x value twice and a different y value, then it's like I'm putting in a chicken and I'm getting some other thing other than chicken nuggets. All right? So, how to tell if a relation is a function if I'm given a bunch of ordered pairs? I want no repeats, no repeated x coordinates. The y coordinates can repeat all they want, but if I have repeated x coordinates, not a function. Okay? For a table, no repeated x values. Remember, for a table, I'm going to make two columns. I got x and y in my table. Okay, x on the left, y on the right. If I have repeated x values on the left, then I'm probably not dealing with a function. And then for a graph, the rule for this one is it must pass vertical line test. And I'll explain that here. A vertical line test means what we do is we pass a vertical line over the graph, okay? So let me give you an example. Here's a graph, okay? Just some random sketch. Now, if I take a vertical line, okay? Here's a vertical line. We'll imagine that this vertical line. Okay, now if I take that vertical line and I pass it over that graph, does my vertical line touch my graph in more than one location at any time? If the answer to that question is no, then it passes the vertical line test and it is a function. Okay, that's the idea. So let me give you another example. Does this graph pass the vertical line test? So again, I take a vertical line and I pass it over my function. And the question is, does this pass the vertical line test? Well, my vertical line is touching my function, or my graph, I should say. It's touching my graph in more than one place at any given time. In fact, right now, it's touching my vertical line 3 times. So therefore, my graph does not pass the vertical line test, which means that this is not a function. So that's what is meant by the vertical line test, okay? How to tell if something's a function from a graph. Okay, so we're going to now apply these to some examples and see if we can figure out what's a function and what's not. So here we go. Is each relation a function? Each one of these, there's 6 different examples here. Each one of these is different, okay? So let's take a look at the first one. We have 4, -3, 3, 2, -4, 2. Is this a function? So this is a set of ordered pairs. We will be looking at just the x coordinates, 4, 3, and -4. Did we see any repeats in x? The answer is no. Okay, we do see repeats in y, but that doesn't matter. We just care about the repeats in x. Because we don't see any repeats in x, this is a function. The answer is yes. Okay, take a look at the table to the right. Here we care about repeated x values. So we look down the x column, we do see repeated x values here. Look at the y coordinates. Those are different, okay? That can't happen. So because of this, this is not a function. The answer is no. For the third one, this is a graph, so it needs to pass the vertical line test. We can just take a pencil or something. Imagine passing your pencil over the graph of this thing. And if the pencil touches the graph in more than one place at any given moment, then it fails the vertical line test. And if we pass this over, do we touch the graph at any more than one point at any time? The answer is no. Therefore, this graph passes the vertical line test, and it is a function. So yes is the answer. Okay, that's how you do that. So let's take a look at the bottom row. With the ordered pairs, is this a function? We look at the x-coordinates, we see repeated 4s here. The answer is no. For the table, is this a function? Again, we look at the x column, we don't see any repeated x's there. We do see repeated y's, but that doesn't matter. We just look at the x's. We do not see any repeats, so that is a function. And we look at the graph. Does that pass the vertical line test is the question. And the answer is no. If I pass a vertical line right there, it does not pass the vertical line test. This is not a function. So that's how you do those. Okay, it's pretty straightforward. You just got to remember how to do it. So, moving along. Now what we need to do is try to figure out what the relationship is in the figures. Okay, now this is kind of like the whole foundation of algebra. People a long time ago, before there was algebra, before there was really math, before people were really civilized in school, they knew that there were patterns out there, and they tried to understand what these patterns were, and that was kind of the dawn of mathematics, the dawn of algebra, the class that you're studying right now. So they saw patterns in things and they tried to explain them mathematically. Okay, so we have an inherent ability to find patterns, recognize them, and then be able to use them. Okay, so in this class right now, what we're trying to do is sort of teach you how to kind of fine tune your born ability to do this. Okay, so in the diagram, take a look at what's going on here. We have 4 figures here, okay? Figure 1, figure 2, figure 3, and figure 4. They give us 4 figures. So the first thing you want to do, like the first thing I do when I look at a problem like this, is I don't even really read the question. I see all those words there, and I just kind of ignore them for a second. I just look, what's happening here as we go from figure 1 to 2 to 3 to 4? Just try to understand, okay? Well, I see rectangles. I see 1 rectangle, and then 2, and then 3, and then 4. Okay? Now, what you want to try to do is try to match. You see how figure 1 has 1 rectangle, 2 has 2 rectangles, figure 3 has 3 rectangles, figure 4 has 4 rectangles. That's important because once I make that connection, then I know that figure 10 would probably have 10 rectangles, right? And figure 152 would have 152 rectangles. That's an important distinction. That's a good connection to make. You always want to try to relate the figure number to the thing that's changing in the figures, okay? So the number of rectangles matches the figure number. That's a very important thing to know. Okay. Now, I also see that these rectangles have a height of 6 and a width of 1. Okay. So that's true all the way through, right? Like figure 4, I see a height of 6 still, and then each one of these rectangles has a width of 1. Okay. So now I can read the question because now I already understand some stuff. It says in the diagram below, what is the relationship between the number of rectangles and the perimeter of the figure they form? So I just read this word perimeter. I guess I better remember what perimeter is. So perimeter is the distance around an object. So I gotta know the length of all of the sides, and then I gotta add them together. Okay, so represent this relationship using a table. So that's why the table is over there on the right, I guess. Words, so I gotta describe what's going on. An equation, so I gotta come up with an equation somehow. And a graph, so we gotta make the graph. Okay, so we can do all that. So the first thing I wanna do is come up with the table. Okay, now when you guys make these tables in this section, what we wanna do is come up with first column, so the left column is gonna be figure number. So that's our first move. The second column will be the number of whatever's going on. Okay, so in this case, we're changing the number of rectangles. Okay, and then the perimeter. So, and really, we could go about this a slightly different way, actually. Um, actually, let's do that. Let's do that. Let's change that middle column. So let me get rid of this instead of calling it number of rectangles, because we already know that the figure number and the number of rectangles are the same. So we'd actually be writing the same number twice, and that wouldn't really make much sense. So instead of doing that, let's call the figure, we have figure number for the first one, which is the same as the number of rectangles. So then let's call this middle column here a process column. Okay, that's where we're going to do some math. And then let's call this last one the perimeter. Okay, because that's what we're looking for. The number of rectangles in the perimeter. Okay, so we have figure number, which is really the number of rectangles, the process, and then the perimeter. Okay, so they gave us 1, 2, 3, and 4. We already know that. Now, what is the perimeter of the first figure? Well, we know it's a rectangle, so we know we have 6 and 6, and 1 on top and 1 on the bottom, right? So if we add all those together, we have 12, 14. So we know the perimeter over here is 14. Now, on the second one, we have 6, which means we have 6 over here. Now, on top, we have 1 and 1, and on the bottom, we have 1 and 1. So it's 1, 2, 3, 4, plus 12 on the sides, right? So we have 4 plus 12, which is 16. Now, for the third one, we have the 6 and 6 again. So we got that 12 again. And then we have 1, 2, 3 on the top, 4, 5, 6 on the bottom. So we have a total of 12 and 6, 18. So if you look at the perimeter, you can see a pattern forming, right? We're always looking for patterns here. So we have 6 and 6 again here. That 12 is still there, right? And that's important. We need to see that. And then 1, 2, 3, 4 on the top, and 1, 2, 3, 4 on the bottom. So that's 4 and 4, that's 8. We have the 12 on the sides. That's 12 plus 8, 20. We can kind of see that already from the pattern that was forming, okay? So all about patterns. What did we see happening as we were filling those things in, as we were thinking about what was happening here? Well, what was happening was we always had something. We always had the 6 and 6 on the sides, okay? This and this were always here. This and this, this and this and this. The 6 and the 6 were always there on the perimeter, okay? The 2 times 6, 2 6s were always there. So I'm going to say 2 times 6 plus. Those were always there. 2 times 6 plus. 2 times 6 plus. 2 times 6 plus. Those are all 12s. Those are always there. Okay? Now, what was changing each time? Well, it was the number of ones that we had across the top and down on the bottom, right? So really, how many ones do I have in the first figure? I have one on top and one on the bottom. There's two. How many ones do I have in the second figure? Well, one on the top and one on the bottom for the first rectangle, but then there's two rectangles. Okay. How many ones do I have on the top and the bottom for the third figure? Well, one on the top and one on the bottom, but then there's three rectangles. Okay. So there's always an addition of how many ones? The answer is two. So in the first figure, there's two ones for a total of two. In the second figure, there's still those two ones for a total of two, but now we have two rectangles. In the third figure, there's still those two ones in the first rectangle for a total of two, but now we have three rectangles, okay? So what we're trying to do is we're trying to come up with a way to incorporate the figure number into the process, okay? So what I'm saying is we have the two from the top and the bottom, the one and the one, it makes two. And we had one rectangle, so 2 times 1. So if we were to do that math here, we have 2 times 6 is 12, plus 2 times 1 is 2, 12 plus 2 is 14. Now, we have the two ones for a total of 2 in the second figure times two rectangles. 2 times 6 is 12, 2 times 2 is 4, 12 plus 4 is 16. So we got the right number there, okay? So then in the third one, we have 2, the 1 and the 1 for the first rectangle, but then we have three rectangles. 2 times 6 is 12, 2 times 3 is 6, add them together, you got 18. So then 2 times 4 rectangles. 2 times 6 is 12, 2 times 4 is 8, 12 plus 8 is 20. So it seems like we have the process right, okay? So it's important that you do that. It's important that you have that middle column to help you see this pattern that's happening here. The 2 times 6, that's always there. And then the 2 times, and then 1 and 2 and 3 and 4, that's matching this figure number that we're on. So now if I asked you what would figure number 27 look like? Well, we know there'd be 27 rectangles. So I could write 27 on the next row down, and you would hopefully understand that it would be 2 times 6 plus 2 times 27. And then you can do that math and know what the perimeter would be. Okay? And that's the power of what we're doing here. That's the power of algebra. Is once we recognize the pattern and we break through and break the code, then we can start doing whatever we need to do with this particular pattern, okay? So what we're going to do is we're going to now come up with the equation. We can let the figure number be whatever it wants to be, okay? So whatever it wants to be would be the letter n, any figure number, n for number, okay? Now the 2 times 6 is always 2 times 6, which is 12. But now the figure number is whatever it wants to be. So we have plus 2 times n. Okay? So then the perimeter would be 2 times 6 is 12 plus 2n. All right? So that's your expression. So now if I wanted figure number 172, that would be n is 172. Then we plug in n is 172, and you got your answer. So our equation now, if we say the perimeter is y, okay, and the figure number is x, then our equation would be y, the perimeter equals 12 plus 2x. And we're done. That's our equation. Okay? That's how that works. And that's how you do algebra. That's where these equations that we are writing come from. So in words, what happens? Well, how did we come up with this? We're going to add 12 to what? 2 times the figure number. Okay, that's it. That's what we're doing. Okay, ordered pairs. Well, we can read them right off the table. We have 1, 14. We have 2, 16. We have 3, 18. We have 4, 20. And we could continue if we wanted to, because now we broke the code. We have the equation. We have an expression sitting there. We have everything we need. Okay? Now to make the graph, we have no negative numbers, so we would put the axes in the lower left-hand corner. The figure number would be there, and the perimeter would be there. Okay, now we need to pick a scale that's going to work here. So we can go by ones for the figure number because we only went to 4. All right. So I'm going to mark 1, 2, 3, 4. I'm going to mark here 5, 6, 7, 8, 9, 10. All right. Now the perimeter, I got to make it to 20. So I probably should go by 2s. So I label that by 2. And then 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, now I'm going to make my dots. So ordered pairs. I got 1 is here, and then 14 is already all the way up here. 12, 14. 2, 16, right there. 3, 18 is right there. And then 4, 20 is right there. There you go. That's how you do that. Okay? So it said represent using a table. We did. Words. We did. Equation. We got it down there. And a graph. We just did that. So we're done. Okay? So we'll stop there for this one, and we'll pick it up next time.